All right, so what we're going to be looking at now is that we're going to be looking at probability and odds more than anything else. So we discussed about sample space and seeing how many total opportunities there are. So now we're going to be looking at you know probability and odds and how many what's the chances of us winning something or losing something. But first off, we're going to be looking at uh, a little question to start, and it deals with birthdays. Everybody likes their birthdays. So the first thing, here's the question. How many people are needed in a room so that there's over a 50% probability that two people will share a birthday? Now this is called like the birthday problem or the birthday paradox. And the reason it's called a paradox is because the answer might not be what you think it is. And so what we're going to be looking at is, with this, we're assuming that it's not a leap year, okay? Which all that means is that we're saying that there's 365 days in a year. We're not going to take that, that one day that's added, not always every fourth, but, occasionally, everything. And the other thing we're assuming is that there's an equal number of people born every day of the year. That's not 100% true. There is some change here and there, but we're assuming that everybody in the world, there's an even number born across the way. Okay. Now the question is, so first thing you should guess, okay, how many people do you think would be needed in a room for you to have two people share a birthday over 50% of the time? All right. And you're probably thinking, well, there's 365 people, or there's 365 days, so if you have half of that, that'd be every other. That seems right? And that would be, like 183. So about 183, and I'm going to tell you that is not correct. That is way, way, way high. Actually, the probability of that would be probably pushing up in the 90s, maybe even 99. It's way up there. Okay. And actually, the number is a lot smaller than you would think it would be. So for this type of problem, one of the easier ways to think about it is to look at it as the probability of people not sharing a birthday. Okay, what's the probability of them not sharing a birthday? And then what we do, since they're mutually exclusive, that means if you put them together, or if there is people sharing birthdays, then that means that then the other one isn't true and everything. Okay, so if you were to add up the probability of each, you get 100%. So what's the probability, if you have one person in the room, what's the probability that two people share a birthday? Or do not share a birthday? Right, because we're looking at the negative. So what's the probability of them not sharing a birthday? Well, that would be, if there's one person, it would be 365 over 365, or 100%. There's a 100% chance that two people do not share a birthday. Makes sense, there's only one person in the room. Now, the second one, we add a second person. So how many different days could that second person be born on so they don't share a birthday? Well, if the first person is born on January 1st, then the other person can be born on any of the other days. So that would be 364 days out of 365. And now we look at the third one. Well, it's going to be one less, 366, or 363 over 365. 4, 362 over 365. And 5, 361 over 365. Okay. So those are the probabilities of people not sharing a birthday with each other. Okay. Now, since these events are independent of each other, it means that you don't need one to be true for the other ones to happen. Okay. We multiply these together to be able to find what's the probability of all 5 of these occurring. When we multiply these together, we get a number approximately 0.973. Okay. That is the probability of people not sharing a birthday. 5 people not sharing a birthday. What you would do here is then you would subtract it by 1. Okay. And that gives us basically a 2.7%. So there's a 2.7% chance that if you have 5 random people, they share a birthday. So thinking of this another way, if you get 5 groups of people and you get 100 of them, 105 groups of people, all right, 3 of those groups will have 2 people that share a birthday. And there might even be more, there might be less. Okay. Again, probability, since we're doing theoretical, this is what it should be. Experimental is what it actually is. Okay. But theoretical is what's like, if in a perfect world, this is what it's going to be, but this cruel, cruel world is not perfect, so theoretical probability doesn't always work. But anyway, this gives us an idea. Now, if you were to take this and continue this and keep adding people, so if you wanted the sixth person, that would be 360 over 365, then you would just multiply this number into that 0.973. And then you'd keep doing that over and over, keep adding people, keep adding those fractions. And if you were to keep doing it, you'll see that you end up finding that the probability in which two people will share a birthday, when that occurs more than 50% of the time, happens at, drum roll please, 23 people. So if you get 23 people in a room, there is over a 50% chance that 2 of them will share a birthday. 23, that's it. Just 23. That's crazy. But if you think about it, think of your groups of people, like if you've ever been in a class of around like 30 people, more than likely you are probably sharing a birthday. Okay? And it doesn't matter which. I mean, sometimes there might be multiple, and it just happens. But over 50% of the time, 23 people will share the same birthday. It actually comes up to about 50.7%. Now, probability. What probability is, it's chance over outcomes, total outcomes. Okay? Or another way of thinking it is the positives over the total. So if you had a die, how many total outcomes are there when you roll a die? 6. Okay, I want to roll a 4. How many 4s are on a die? 1. So that means there's a 1 in 6 chance of me rolling a 4. Now, for my first roll, I wanted a 4. For my next roll, I want an even number. And for my last roll, I want an odd number. How many even numbers are on a die? 3. 3 over 6. How many odds are on a die? 3. 3 over 6. And if you wanted to find what's the probability of me rolling a 4, an even, and an odd, okay, in 3 rolls, you would multiply these together. Multiply, multiply. That would get us a 9 over 3 cubed, which reduces down to about 1 over 24. 1 over 24. So there's a 1 over 24 chance of me going 4, even, odd. Okay, that's probability. Now, odds. Odds are a little different. How probability was the positives, or what you want, over the total. Odds are positives, and then it's a ratio. So you'd put a little colon here. Negatives. Okay. Now, if you've ever been to or if you ever heard people betting on anything, they might say, "Oh, there's 3-to-1 odds. It's so good," or "There's 7-to-1 odds," or 1,000,000-to-1 odds. Those type of things. Okay. Basically, what it is, it's like the odds of them winning or losing to the times them win. So if I say there's 3-to-1 odds, that's different from the probability. 3, you could say 3 is the positive outcomes and 1 is the negative outcomes. Okay. So if you were to play a game, okay, 4 times, 3 times you'll win, once you will lose. So that means your probability would be 3 over 4. When you add the two parts of an odds together, you get the total number. Okay. Now, there is, when you go to different places, there are some fluctuating. It depends on the wording that they use, but this is basically what odds are. It's the positives to the negatives, or it could be negatives to positives, depending on how you want it. But if you add them together, you're going to get the total. All right. So this is probability and odds. There's a whole branch of mathematics. You can take classes on just probability theory, which is a wide range, and it's a ton of different stuff that you can look at.